Day 8, we're getting a little deeper into section 5.4. We're going to now take some derivatives of some exponential functions, but those exponential functions are all going to be in the form e to the x for right now. We'll add in other bases later. Pardon me, and then we're going to work on some extreme and some inflection points because we haven't in a while. So, derivative of e to the u times du over dx. So what we're saying here is that u is a function of x. So if u is a function of x, then the derivative of e to the u is going to be e to the u, and the derivative of that power then is going to be du over dx. So slope of the tangent line. If I want to find slope of the tangent line, I'm ultimately going to need a derivative. So what we're really looking for here is we're looking for f prime of 3. That's what we ultimately want in order to find the slope of that tangent line. So let's take the derivative. So the derivative of this function, f prime of x. So what do I have? I have e raised to the negative 2x. So the derivative of e to the negative 2x is e to the negative 2x times the derivative of negative 2x. So what I really have, negative 2 over e to the 2x. If I want to find f prime of 3, we'll plug that in. Looks like negative 2 over e raised to the 6th power. And yes, you can make a decimal out of it, but if you could make a decimal out of it, we should have done this problem with the calculator in the first place. Second one. Derivative of e raised to the negative 1 over x squared power. So let's rewrite it before we start, because I'm looking at this thing. If I go to take the derivative of that power, I'm going to need quotient rule. I don't want to do that, so we're going to take the derivative, let's see. So this would be e raised to the, well, you know what, let's live with it as it is. I don't think we're going to be able to change it very much. But now that I look at this, couldn't this x squared be moved to the top with a negative exponent? Let's change it. D over dx. So what do I have here? I've got e raised to the negative x to the negative 2nd power. So now we're going to take the derivative of that. So derivative of that, let's see, derivative of e is going to be an e to that same thing I started with. And we're going to multiply it then by the derivative of that power. So the derivative of that power, positive 2. Negative 2 times negative would be positive 2, pardon me, x to the negative 3rd. So now the challenge will be to rewrite that so we don't have any negative exponents. So to fix negative exponents, I know I'm going to have to move that x to the negative 3rd to the bottom. It looks like the only thing I'm going to have left on the top is a 2. I'm going to move the e to the negative x squared to the bottom and make it e to the positive x to the negative 2nd power. And I'm going to move the x to the bottom and make it x to the positive 3rd power. And now the only thing I have left is I have a negative on that x in the exponent. So if I want to clean that up, how about 2 over? The x cubed I'm not going to touch. And the e is going to stay the same, but we're going to change the power on its exponent, on the x in its exponent. How about e to the 1 over x squared power in that denominator, and that should take care of all of our negative exponents. Kind of nastiness to take care of that, but we've done our derivative. So derivatives with e's are kind of nice. We generally kind of like them. So let's look at 3. So I'm looking at this derivative. Looks like a quantity. It's a single term made up of 2 things being multiplied, so I'm feeling like a product rule coming on here. So product rule, derivative of e to the negative x. So let's do e to the negative x. So first, times the derivative of natural log of x. Derivative of natural log of x would be 1 over x. Plus, I'm going to take that natural log of x, and I'm going to multiply it by e, the derivative of e to the negative x, which would be e to the negative x multiplied by negative 1. So as I look at this, and one of the things that you're going to start to see a pattern of is every time you have e's involved in a product rule or a quotient rule, you're going to have common terms. I notice that there are 2 terms written in red. They both have an e to the negative x in common. So let's factor out an e to the negative x from both of those terms. First term will leave me 1 over x. Second term, whoops, sorry, it won't be plus. Looks like it'll be minus natural log of x. And if you wanted to, we could do common denominator. We could write the e to the negative x in the denominator. So how about e to the negative x times 1 minus x natural log of x over an x, common denominator in there. And now instead of leaving the e to the negative x on the outside in the numerator, how about if we just move that e to the negative x? Sorry, it won't be negative anymore. Let's move that e to the x to be a part of that denominator. So there's our derivative with everything cleaned up the way that it should probably be. So there's your first goal. So first goal was to take care of exponential functions with e to the x in it. Now second goal is to review a little bit of extrema and inflection points. So find extrema, find inflection points for this particular function. So x squared times e to the negative x. So again, I see a single term. I see that it's going to require me to multiply x squared times e to the negative x. So it looks like we're going to need a product rule. And I've got e to the x involved. So there's going to be some patterns that develop. So let's look at the first derivative. So I'm going to start looking at my extrema. First derivative, x squared times e to the negative x times negative 1. So how about if I just write this negative e to the negative x plus e to the negative x being multiplied by a 2x. Okay, now again, two terms. They both have an e to the negative x in common. They also have an x in common, but I'm going to hold off on that right now. Always, if you can, look to factor out your e to the negative x's out of these quantities whenever you can, and here's why. Negative x squared plus 2x. If I right now said, all right, I need to find my critical numbers. Critical numbers. I'd set this derivative equal to 0. So if I did that, I'd set e to the negative x equal to 0, and I'd set negative x squared plus 2x equal to 0. Well, e to the negative x equals 0. If you picture that e to the x function that we've drawn, or even e to the negative x function that we've drawn, it can't hit the x-axis. It has a horizontal asymptote at y equals 0. So you will never get any critical numbers out of setting an e to the x equal to 0. It's just not going to happen. You have to have another term in there somehow in order to get a solution. So now if we go over here, negative x minus 2 is equal to 0. So it looks like x equals 0 and x equals 2. And then I could go through and I could set up my intervals. Set them up, test them in the first derivative, tell me about my original function. So if I go up to my first derivative, if I plug in a negative number, e to anything is going to be positive. So this e to the negative x thing is always going to turn out positive. So what we're really looking at is negative x squared plus 2x. When is that positive and when is it negative? Well, I know that's a parabola that's opening downward. If it's a parabola that's opening downward, that means it's going to be negative and then positive and then negative again. So my function is going to decrease, increase, decrease again. So we're looking at a relative min at the point 0 something, and we're looking at a relative max at the point 2 something. How do you find the something? Go back to the original function. So if we go back up to the original function, plug in 0. E to the 0 is going to be 1. 0 squared is going to be 0. So I've got a relative minimum at the origin. And plug 2 in. 2 squared is 4. E to the negative 2 power, this is a 4 over e squared. So we've taken care of extrema. There's a little bit of a review. Inflection points, a little bit more exciting. Inflection points, I'm going to need a second derivative. So I'm going to take the derivative of this thing, second derivative. So we've got first e to the negative x multiplied by the derivative of negative x squared plus 2x, negative 2x plus 2, plus the second, negative x squared plus 2x, times the derivative of the first, which would be e to the negative x times negative 1. Negative e to the negative x. So I see now two terms. What do they have in common? They both have an e to the negative x. So let's factor that out. Negative 2x plus 2. We've got extra negatives here. So how about plus x squared minus 2x? So if I'm looking for inflection points, x squared minus 4x plus 2. And I don't think that thing is going to... So critical numbers, we know we're not going to get any critical numbers out of e to the negative x, so we don't have to worry about that. So what we really care about is when is x squared minus 4x plus 2 equal to 0. That's not going to factor, so I'm looking at probably quadratic. 4 plus or minus 16 minus 4 times 1 times 2, 16 minus 8 divided by 2. So I think we're looking at 4 plus or minus the square root of 8 over 2. And I think once we get to that point, you could probably turn that into a decimal easy enough. I know that x squared minus 4x plus 2 is a parabola that's opening upward. We just found out it's going to hit the x-axis 2 times, so we'd end up with 2 inflection points, and they'd be at x equals 4 plus or minus square root of 8 divided by 2. If we needed better detail, we could get our calculator out and find it.